Marty. Oh my god, you scared the shit out of me. What the hell is going on here? This time, I think I figured it out. Just give me 1 second. Now look, if I plug this in here, and here. Wait. Well, I don't see anything happening though. Well, I guess still better than last time we blew the circuit up. Wait, look. I'm plugging my rookie mistake. I don't plug in my battery. I don't think I quite get it, but all of this just for 2 blinking LEDs? Yes. Isn't that amazing? You don't get it, but this circuit is theoretically impossible. But because we live in a realistic, real world, nothing is perfect. That's why this circuit behaves how it does. Wow. Wow, that's totally uncool. Okay, just dress your ass up and we're going out in 5 minutes, right?
Thank you guys for watching the video. A Chad engineer once said, every great project starts with a blinking LED test, am I right? All jokes aside, you probably already heard of this circuit, but if you haven't heard it yet, this circuit here is called the astable multivibrator oscillator, which was first publicized by Abraham and Bloch. This circuit was initially designed with vacuum tubes in the 1920s. This is what it looked like. Quite impressive, huh? Well, if that doesn't impress you, I don't know what will. Probably wondering to yourself though, how is this circuit theoretically impossible? The answer is that in theory, everything works too perfectly in a sense. In a sense that this circuit would not be able to oscillate in a perfect condition. What this basically means that the 2 LED here would not alternatively blink to each other, right? So the outputs doesn't oscillate. That's why it's called the oscillator. So the beauty of the circuit lies in the imperfection of the real world, whereby the imperfection of itself is what makes the output of the circuit possible. Let me give a try in explaining the circuit. This is the schematics of the astable multivibrator oscillator. What does it consist of? Well, it consists of 2 transistors, Q1 and Q2, 2 capacitors, C1, C2, and 4 resistors. Simple, right? The transistor in this circuit are just used as a switch. Which gets triggered by a threshold voltage, VTH, of 0.7. All this basically means that the transistor turns on when the threshold voltage at the base is 0.7 volts, and it's off when the base is less than 0.7 volts. So this is on. When transistor is on, then the switch will close. This is on, and when the transistor is off, then the switch remains open. That's all the transistor does in this circuit. It acts as a switch and gets triggered by a certain voltage at the base, which in this case is 0.7 volts. However, the key component of the circuit is actually these 2 capacitors here, C1 and C2, which supplies the base voltage of each transistor. You see? In an ideal setting, these capacitors would not add much to the circuit. But in reality, these capacitors have tolerances. What this basically means that the capacitance of each capacitors would vary slightly of each other. And because of these discrepancy, it creates the fast switching of the circuit. Let me further elaborate. So if we were to try to reverse engineer this, we know that the outputs of the circuit oscillates. All this basically means that one of the transistors, when it's on, the other must be off, and vice versa. So let's just take an example when Q1 is on. Looking at this circuit, when Q1 is on is when this base voltage is 0.7 volt, which is the case. And when that base voltage is on, there's current flowing through here, right? As now the switch is closed. And for the off condition, let's take an example of Q2 transistors, is when the base of this voltage is less than 0. Is less than 0.7 volts. So what this means is that this switch over here is open and it's not touching. So there's no current flow through here. Alright? Now the interesting bit is that the base voltage in this circuit is dependent on these capacitors. In theory, these capacitors charge up at the same rate, which means that in turn, the transistor will turn on at the same time. In reality though, one of the capacitors would charge up first, then the other. So that's where the magic actually happens. Looking at this diagram, Q2 is off, Q1 is on. So there's a current flowing through here, but no current flowing through here. Let me do a different color. The magic happens is when the other capacitor catches up and starts supplying Q2 with 0.7 volts. What happened is that now this is charged 0.7 volt, which then opens this whole loop, which closes this switch, means that the transistor is now on. Then the capacitor C2 over here is now shorted to 0 volts. As the energy stored in the capacitor stays the same due to the conservation of energy, the only change is now that the charge has been flipped. So before, the capacitor C2 was 8 volts at the anode side, the cathode side was supplying 0.7. But now it's shorted, it has become, anode of the cathode becomes 0 volts, right? As I mentioned before, the energy stored in the capacitor stays the same. So the only thing that happens here is now that the charge has now been flipped and there'll be a reverse voltage, which in turn makes this 0.7 volt becoming negative 7.3 volt. And now the base of Q1 is at negative 0.3 volts, which turns off the transistors and opens the switch, and no current flows through here, right? And now Q2 is on, however Q1 has now been turned off. The key point here is actually the reverse voltage. When one of the transistors is on, it shorts the anode of one of the capacitors, which then reverse the voltage of the base voltage of the other transistors, which turns off the other transistors. And now it's switching, right? The cycle begins again when this base voltage starts charging up to 0.7 volts. Hope this helped you a bit in understanding the circuit and the reason why it's theoretically impossible. And to recap, why it's impossible is because of the tolerances of the capacitors.